Hello friends, I welcome you to this interesting discussion. So this is where we're going to look at simple harmonic motions, that is in physics. So a simple harmonic motion is simply an interesting discussion where we're looking at an object moving back and forth from one point to the other. It is repeating the same motion. So this is simply known as a simple harmonic motion. So you can also say that this simple harmonic motion is simply a kind of motion where an object is moving. It is oscillating back and forth about a mean position. So as it is moving like about a mean position, which is also known as what, an equilibrium position. Okay, an equilibrium position is, we can divide the motion into two. So as it moves, let's say from point A to C, mean that it has to pass through the point, let's say B, which we'll label as the equilibrium position or the mean position. Okay, this is where now we have an object to be like moving at equal distance from both ends A and C, which are also termed as the extreme points. Okay, so I'm writing the definition there for more understanding and reference when going to the same simple harmonic motion. Okay, so we have quite a good number of examples of simple harmonic motions. We can give an example of a cradle. So as it is moving, it is repeating its motion. So that is an example of a simple harmonic motion. You can give an example of a pendulum, which is an object tied on a string which is oscillating back and forth. That's an example of a simple harmonic motion. You can give an example of a string vibrating. That's an example of a simple harmonic motion. You can give an example of a spring. So for more details, let me draw this to represent the simple harmonic motion. So we're going to have, from this point, it is moving to the other end. Then when it reaches at the other end, it starts coming back. So this is a simple harmonic motion. Then there's a point which is known as the mean position or the equilibrium position. So this is the mean position, and on the other two ends we have the extreme points. So these extreme points are simply furthest point where an object cannot exceed as it is moving, or as it is oscillating, or as it is moving periodically. So I have the extreme point there, and on the other side also have another extreme point, which is our furthest point in this case. So we can label this extreme point as A, then we can label the mean position as B, and as C, the other extreme point. So an object will move from A to B, then exceed to C, then move from C to B, then back to A, just like that. So that is what we refer to as a simple harmonic motion. So that is a behavior of this kind of movements. Now for this simple harmonic motion to be possible, or for an object to move periodically, what we need is simply an application of a force. So it has to be put or pushed from the mean position to one of the extreme points. So meaning that it has to be it needs a force to be applied. Now this same force is simply what we call or know as a restoring force. So a restoring force which is applied on an object moving periodically is known as a restoring force. Okay, so simply known as a restoring force. So I'm going to give an example of a pendulum. So I'm going to draw a pendulum for reference sake. So I'm going to draw a pendulum there. So this is how a pendulum is. So we have a line like that, then we have the extreme points there. So this is an extreme point, another extreme point, and the mean position. So this is the equilibrium position, which can also be called the mean position. Okay, so it is also called as the mean. Then we have the extreme point there, extreme position, and also another extreme point there. These are furthest point reached by an object which is oscillating back and forth. Now from the mean position to one of the extreme points, there is simply a force that is applied. This force is what we term as the restoring force. And again, from the same mean position to one of these extreme points, there is displacement there. So there is overall change in position. And what we need to know is that this same force is simply directly proportional to the displacement of an object. So I can say that the force mathematically is direct proportional to the displacement. Now, in as much as they are direct proportional to each other, what we know is that they are in different directions. I mean, not necessarily different directions, they are in opposite directions, meaning that we have that our force will be direct proportional to negative of the displacement. Now, to change this proportionality sign to equal sign, we're going to multiply with a constant. So this is a constant of a force, which is k, then multiplied by y, like that. Okay. So what we now do is that we're going to simply apply this Newton's second law of motion, where we have that the force is simply the product of the mass and the acceleration. So upon applying the Newton's second law of motion, we simply yield the force to be the product of the mass and the acceleration. So I mean that this mass and acceleration being the force is now what we're going to simply substitute over there is the force in our equation of proportionality there between the force and the displacement. Okay, so that's what we're going to substitute there. We're going to substitute ma. Now we have that f is simply equal to negative ky. So where there's f, we can put ma, which is equals to negative ky. Now what we do next is we're going to take what is on the right to the left. Upon doing that, we're going to get a positive value, so it will be ma, which plus ky, which is equal to 0. Okay, then again, making reference to kinematics, we have that the acceleration is simply the rate of change of velocity. It means that we're looking at how an object is changing, like the speed with respect to time. Now this is towards a particular direction, and again, this velocity is simply the rate of change of displacement. You're looking at the position. How are the positions changing? So you're looking at an object changing from one point to the other, and that is towards a particular direction. Now as that is done, there's simply a time being involved, so we have to have the rate of change of displacement for velocity. So which means that since velocity is the rate of change of displacement and acceleration is the rate of change of velocity, it will therefore give us acceleration to be the rate of change of displacement twice, meaning we get the second derivative as the rate of change mathematically is known as derivative. So we get the derivative, which is the second derivative of displacement, for us to simply have acceleration. So we're going to have acceleration equals the rate of change of displacement over the time. In displacement, mean velocity will be equal to the rate of change of displacement over the change of time. So I mean that acceleration will be the rate of change of displacement twice with respect of time, like that. So the delta symbol will be changed to d squared y dt squared, that is by use of calculus. So now this is what we're going to substitute in our equation ma plus k, which is equals to, so we're going to have m, right, the second derivative there, which is just same as acceleration, then say plus ky, which is equal to 0. Now we are going to now divide through by m, so that we leave the second derivative with only a coefficient of 1. So we're going to divide through by m. So we're going to divide the second derivative with m, divide the ky with m, and also 0 by what? By m. So this will give us m by the second derivative. This is over m. Then you have plus ky over m, which is equal to 0 over m. Now the m and the m will cancel out, leaving us with the second derivative there. Then you have plus k over m y, which is simply equal to 0. Now what means that k over m, constant of the force and mass, is the same as the angular frequency squared. So this is same as angular frequency squared. Now angular frequency simply represents how quick it takes an object to complete one circle, or maybe to move from point A to point, which is the main position, then to point C, and then from point C back to point A. So means that our second derivative will plus what is k over m substitute with the angular frequency squared. So we're substituting the angular frequency squared multiplied by y, which is the displacement. Then this is equal to 0. Now what we have here is simple, what we know as the differential equation of a simple harmonic motion. So for now, we're done with part 1. We'll cover part 2 very soon. We're going to continue from where we have ended from here.